Hey everyone, this is Jayant, an aspiring AI engineer. Have you ever thought why eigenvalue and eigenvectors are used in PCA? Today I am going to explore the problem formulation of PCA and I will derive the eigenvalue eigenvector equation for you. If you really want to stand out as a data scientist or a ML scientist, this video is for you because it's crucial to understand the mathematics behind PCA. Let's dive in. It will be very fun. I'm very excited. Guys, let's see what PCA actually solves. PCA aims to find the directions, nothing but the unit vectors. Why we are calling the unit vectors are directions? Because their magnitude is one. The whole focus is to give us the direction along which the projected data exhibits the highest possible variance. Why we are concerned with variance? If you couldn't understand this sentence, please go and watch the videos of Nitish sir from Campus X. Sir greatly explained the PCA in three parts. Please go and explore them first and come to this video. I'm giving the mathematics depth of it. Why we need eigenvalue and eigenvectors? See, let's go to problem formulation. I'm taking two features of the data sets. I'm considering only two features. One feature is along x direction and one feature along y direction, as you can see on the screen. And I'm projecting any one of the point, let's say ui, I'm considering it as ui, and the unit vector, on the unit vector, as you can see on the screen clearly. And mean also will be there, right, for this data. And that mean is, you can see mu I have represented with mean, and its coordinates are mu x and mu y, because along x direction variance will be, mean will be there, and along y direction means the coordinates of y, nothing but the features. Feature 2, the mean of feature 2 is represented as mu y. Now see, what is variance? What is the formula for variance? What is it? Nothing. Why? How can we understand variance? Variance is nothing but the spread, how the given data was spread along a certain axis. This formula tells us how the given data is deviated from the mean, because after considering the mean as a statistical technique, we considered the variance, and the variance formulated as, you can say, sigma 1 to n mu I minus mean whole square divided by n. Now we are concerned about the projected data, right? Now variance of this projected data is equal to, you can see on the screen, V is equal to, I just projected dot product of this vector mu I. Why I am doing the transpose? Because to do the matrix multiplication, I have represented a vector as a matrix. I will show you in the, as along the way. I will show you that. And mu I, ui means our data projecting on a unit vector, subtracting, because we have to subtract, right, with the mean, and the mean also we will be have, we should project, right? This is the problem formulation. Now let's simplify it. See, I just written the square as two parts here. See, same parts written in two parts, and I just exchanged this, because we can exchange in dot product, right? I just written V transpose into UI for the matrix multiplication to do the dot product. See, and also exchange this term, and I asked is, I written this term down bottom. You can see my cursor, right? And I just multiplied, guys. I only just multiplied each and every term. See, V transpose UI dot U trans multiplication of this with this with this. You can see this is the first term, second term, third term, and I just taken common VT on the right side, left side, and V on the right side. See, this is a complete simplification of this. See how we are getting. We are just kept V transpose outside and V this side, and the whole part I'm considering it as C. Because it is a scalar, right? You dot product, you will give a scalar. That's why I have written as a C, some constant C. See here, we are simplified our problem formulation to this: v transpose v is our unit vector, its transpose c into v. Now what is our goal? Our goal is to maximize this variance with the constraint. Why we are having a constraint? Because it is a unit vector, we have to consider that, right? It is a unit vector, that's why I written norm is equal to, norm is nothing but modulus. I think you can understand it. See, this is norm. See, now let's expand. I'm trying to find out the dot product of V transpose into V. What it will be? V modulus of V. I hope you know the formula for dot product. A dot B is equal to modulus of A modulus of B into cos theta, angle between A and B. Because these are same vectors, theta will be 0. And V transpose, modulus of V transpose is equal to modulus of V whole transpose, right? And modulus of V is 1, we know, because it is a unit vector, and you can see here, and we got this as 1. Now our constraint is V transpose into V is equals to 1. Now we have two functions like f of x and g of x equal to c. Now we want to maximize the f of x using this constraint, subjected to this constraint, V transpose into V equal to 1, right? I hope you are getting what I have told. Hope you understood the problem formulation and the simplification. If you have any doubts, please let me know in the comment section, guys. Please let me know. Now let's get in. See, our objective is to maximize this variance subjected to a constraint V transpose dot V equal to 1. Such problems, the real magic comes here. The Lagrangian multiplier. He is the person who is helping us to do this maximization. See, such problems of constrained optimization might be formulated as a unconstrained optimization. Now we are, it became an optimization problem. For value of v, it will be once the variance should become maximum, right? Now what value of v, which vector I have to take so that variance will be maximum? It became an optimization problem now. See, what is Lagrangian is telling us? If you if you want to maximize a function f of x subjected to a constant g of x equal to c, like v transpose into v equal to 1, we introduce a Lagrangian multiplier lambda. And see, it will be written as like this: Lagrangian will be written f of x minus lambda into g of x minus, this is the Lagrangian multiplier. We have constructed it. Now let's apply for our problem. The sign of lambda doesn't matter. How we will solve? We then solve the system of equations. We get two system of equations on solving these two. See, two, we are, why we are equating these to 0? To get the stationary points, right? To get the stationary points. Now in our case we want to the solution. See, in our case we want the to maximize the variance v subject to a constraint v transpose into v equal to 1. Our Lagrangian will be, this will be our Lagrangian, right? Now let's solve for the stationary points. Why I am trying for the stationary point? If there is a stationary point, then it could be a maximum or a minimum, right? It could be a maximum or a minimum. It could be maximum or minimum. That's why we are searching for the stationary points. For stationary points, we have to equate derivative to 0. That's why that is what I have done. See, dou L by dou V with respect to V. Now this is partial derivative, right? I hope you know how to do the partial differentiation. We keep one variable as a constant and we derive, we do differentiation with respect to the other. See, I just see the numerical value, right? I just kept, I taken out from the important part, and dou by dou v into v dot v transpose. See, I hope you can, this is very simple calculation, guys. See, now what it will be? Now v transpose dot v, what it will be? What it will be, let's do it. See, v transpose dot means dot product of a dot b, it will be modulus of a modulus of, do cost, theta is 0, right? Theta is 0, I mean cos 0 is 1. Now modulus of v is nothing but modulus of v transpose, therefore modulus of v, what it will be? V transpose dot v is equals to modulus of v whole square. That's what I have written. And it will be, see, I have taken this to the right side, this part to the right side, and negative is gone. I think you can do this simplification, right? Very easy simplification. See, v modulus of v whole square derivative 2v, it will become 2v. I have written it. See, c into 2v is equals to lambda. Now the eigenvector value equation we derived, guys. See, c into v is equals to lambda into v. C is our linear transformation. We are applying on a vector v, and we are able to write this transformation on a vector as a linear combination by taking a scalar. Not a linear combination, we are able to get a lambda, a scalar, and multiplying this scalar with this vector is same as applying the linear transformation on this vector. It is nothing but a eigenvalue eigenvector equation. That is the reason. That is the reason why we are searching for, why we are deriving, why we are finding the eigenvectors, because the eigenvectors contains the vector eigenmatrix. We will get the eigenmatrix, right? That matrix contains the vectors on which the given projected data will be having maximum variance. We are searching for, right, where we want to maximize the variance, and we came up with this equation. What does it mean? The variant, to get the maximum variance, we want a unit vector. Those vectors are present in the eigenmatrix. You go and search there. It is telling like that for us. And it, see, eigenvectors may not be equal to magnitude equal to 1, but they may not be unit vectors. For the simplicity purpose, we considered a unit vector. I hope you understood. It is the eigenvector equation, the vector we are searching for. See, now if you do another derivative, it will be, see, v transpose into v equal to 1 v got. We already know it. There is no use on doing this. Now let's decode what is C. What is C, guys? I'm excited. What is C? I hope you too. See, I am written the C that we have taken. C. This C. How we got this? This is only before I written a C, right? I written only that one C. What is this act? What is this C? Let's decode it. Let's decode it. See. See, this is our C I have written. And what is UA? Our vector I have written in a matrix format, xi and yi. And mu, our mean along x direction means of feature 1 of feature 2, mu x mu y matrix representation. See, I hope you understood this. And see, and I am computing each and every part of this equation of this C step by step. Mu I into mu transpose, nothing to do, just matrix multiplication. Very simple. This first vector xi, and the column multiplying. I hope you know how to do matrix multiplication. Xi square, xi square, xi yi, xi yi. I have just done this, guys. See, you can see how simple it is. I have done for every part here, every part. See, I just computed these calculations. Very simple, guys. Very very simple. Makes me, you can see. I will share the notes also with you. Go through it, you will understand very clearly. If you have any notes, please write in the comment section or reach out to me in the LinkedIn as well. I will give the my LinkedIn ID in the description. Okay. See, mu in the mu transpose everything, and I just see, I just kept all these values, all these matrices in this equation. In this equation, see, everything I substituted in this. See, this matrix subtracted with this, adding this, we will get this. See, xi square minus mu I, see this one, xi square minus this plus this, because we are having this equation, right? Multiply, adding the matrices. I hope you know how to add the matrices as well. See, xi square minus xi u, like this, and this will be the another part, second column this will be. See, and it came out to be this. Our C came out to be this C, because this you can write it as a whole square, right? Xi minus mu x whole square, you can write it. You can also simplify this to this. See, if you multiply this, to 1, you will get this, you will get this. I just wrote the simplification of C here, and we come out, the C come out to be like this 2 by 2 matrix. Let's understand what is. I hope you recognize what is this C if you watched those videos on Campus X channel. See, the covariance. What is covariance? It measures the relationship between two variables. Like we have feature 1, right, and feature 2. What variance will tell us? Variance will give variance of this feature, first feature, and it will give variance of second feature. What if I want to compare the variance of two features? That's where the covariance comes. Covariance gives the relationship between the covariance of first feature and the second feature. If any feature, any number of features, I just consider only two features for this. To explain simply, you can consider any number of features. Any number of features. See, if you get the positive value of covariance, what does it mean? The two features will increase simultaneously or decrease simultaneously. If it is negative, then they obvious, right? If one increase, other will decrease. We have to understand like that. And the covariance matrix, I hope you know what is the formula for covariance matrix. Covariance of x and y, we are considering two features, that's why I have written only for two features. Covariance matrix can be extended to n number of features. N number of features. Please go and watch the video from the campus. Sir explained very 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 clearly. I loved sir explanation, that is why I'm not making video on that. The important part is mathematics, that not sir not told that part. I want to cover, I want to fill this gap. Because here you will become you will become you see, you will be unique, right? When you go for interview, you will be having that confidence. I know the mathematics. In companies, if you get any challenging problem, you should know the mathematics. Then others will be, others will find difficult to solve that problem. You will be, for you it will be very easy, right? Let's see, the covariance matrix is computed like this, it is written like this. And covariance of x comma x is nothing but feature of nothing but variance of x, and this is also variance of x. And the covariance will be written as like this. And the covariance matrix will come out to be 1 by n, means variance xi minus mu x whole square. And this will be like this because I have just written this part here, this part here. These two will be same. It is symmetric. Covariance matrix is symmetric matrix. Understand it. See, this I have written. See, variance of y will be, I hope you can recognize very very clearly. Our C that we have computed here, it is nothing but the covariance matrix. That is the reason, guys. That is the reason. When we are finding the eigenvectors, we find the eigenvectors of covariance matrix. If you know the code, you will understand very clearly. That is the reason. This is what I want to convey in this video. I hope you understood. If you loved the content, if you understood something, if you got any value, please like, share and subscribe. Thank you.